Hi guys, welcome back to another video. So today I have a question that I found from one of my juniors' Introduction to Mathematics exam. So here's the question. First, consider the following sequence that goes 1, 2, 2, 3, 3, 3, 4, 4, 4, 4, and so on and so forth. So we can describe it as one copy of 1, then 2 copies of 2, 3 copies of 3, 4 copies of 4, and so on. Now, we have to show that the nth term of the sequence can be represented by this formula. So if the nth term of the sequence is an, then it is equal to the floor of square root of 2n plus 1/2. Now, a bit of a reminder, the floor function here is the round down function. So basically you round down whatever is inside of this square bracket. Or more rigorously, it is the largest integer that is lower than x, or the number inside the bracket. So the floor function of 0.6 yields 0, the floor of 4.2 is 4, and the floor of pi is 3. So I'm going to give you a bit of a chance to do this question on your own. You can pause it, and then once you're ready, you can unpause it to see the solution. Okay, so first of all, let's take a look at what happens when we plug in different values of n. So let's say if we plug in the first, if we want to find the first 3 terms of the sequence, n equals 1, n equals 2, and n equals 3, then let's check n equals 1. a1 here is equal to the floor function of square root of 2 plus 1/2. Now the square root of 2 is equal to 1.41 something, and if you add half to it, you get 1.91. So the floor function of 1.91 something is 1. Now, what about the second term? a2 here is equal to the floor function of square root of 4 plus 1/2. And the square root of 4 is equal to 2. So we're finding the square root of 2.5, which is 2. And now the third term here is the floor of square root of 6 plus 1/2. And if we plug in our calculator, we get the floor function of 2.94 something, which values a 2. So as you can see here, for the first 3 terms of the sequence, it seems to line up. But why? So to show that this is indeed the nth term of the sequence, let's ask, if you have a certain natural number, let's say k, for which values of n does actually no, that's a little bit too advanced. So let's say I have a uh, a natural number k. All right. So what does this represent? If we were to fix k, so like k is a constant, then the only unknown in this equation is n. And solving for n actually gives us the terms, or the term numbers whose value is equal to k. I'll let that sink in for you. So if we want to find which values of n satisfy this equation, we can actually turn this into an inequality. So if you have, for instance, 4.1, the floor of 4.1, it is equal to the floor of 4.6, which is equal to the floor of 4.99 something. So from this observation, if you want to find the values of x such that this equation is true, then you have to find x such that x is between 4 and 5. Now, if you plug in 4, it does also include 4 is also included in this inequation. That's inequality. I keep saying inequation. So this is the idea that we're going to transfer here. So in order to solve this equation, we can turn this into an inequality. This is equal to, or not equal to, I mean like this is equivalent to the square root of 1/2. The square root of 2n plus 1/2 should be between k and k plus 1, which is also equivalent to k minus 1/2 less than or equal square root of 2n be less than k plus 1/2. Now, because each of these terms are all positive, because we just set k being a natural number, and we know that this number should be a positive number then, because n is the number of terms and blah, blah, blah. So we can square each side of this inequality. So we can rewrite this as k minus 1/2 squared less than or equal to n less than k plus 1/2 squared. We can also divide each side by 2. 1/2 k minus 1/2 squared less than or equal n less than k, sorry, 1/2 k plus 1/2 squared. All right. So basically, these two forms are equivalent if k is fixed. If k is fixed, then you can find n, or actually more precisely, the integer values of n to find which term has the value k. So we're only looking for the integer solutions of n. Now I'll stop here, and then we'll take a look at just the width of this interval. So there's an interval, and we'd like to know how large is this interval. So notice that if we subtract the upper and lower bound, so we get like this, we have 1/2 k plus 1/2 squared minus k minus 1/2 squared. Then this is equal to 1/2 k squared k plus 1/4 minus k squared plus k minus 1/4. Now, k squared cancels out, 1/4 also cancels out. So what's left here is 1/2 times 2k, which is equal to k. And remember, k is an integer, or more accurately, a natural number. So what significance does this result have? So if you plug this into a number line, then you have 1/2 k minus 1/2 squared here, and then we have 1/2 k plus 1/2 squared. Now, this actually passes through a certain number of integers, but how many? Well, the answer is k. There are k integers between these two numbers, and those numbers are exactly the solutions in n of this inequality. I want to give it a different color. This inequality. So you have this number of integers, which is exactly equal to k. And that is like a bit of a rough idea of how you can get one copy of 1, 2 copies of 2, and so on, and basically get k copies of k after k minus 1 copies of k minus 1, and so on. But just in case you're really curious, let's take a look at the just take a look at how you solve this inequality. All right. So if k is equal to 1, then the lower bound is 1 half times 1 minus 1 half, which is 1 half, and you square it, you get 1/4. That's not equal to n less than 1 half times 1 plus 1 half is equal to 3 halves, or 3/2. Squaring it gives you 9/4. So n should be between 1/8 and 9/8. Now, there is only one integer between these two numbers, which is 1. So the only integer solution here is 1. If you plug in k is equal to 2, then the lower bound should be equal to the upper bound of the previous value. So it's 9/8. And then the upper bound is going to be 1 half times 5/2 squared, which is 25/4. Then you multiply by 2, you get 25/8. Now, how many integers are between these two numbers? Well, this is 1 point something. It's not really important. This is 3 point something. So how many integers are between these two numbers? Well, there are two values, 2 and 3. And these are exactly the solutions of n, or the integer solutions of n, that satisfies the inequality when k is equal to 2. So that's a bit of a rough sketch of what the final stage of the proof should look like. But from here on, I'm going to challenge the viewers to try to conclude the proof on their own, because obtaining the proof from this point shouldn't be too difficult. So yeah, it's been a fun problem actually. So I think that's all from me today. I hope you enjoyed the video. Leave a like and subscribe if you do enjoy it. And see you in the next video.